I hope this teaser video triggered your interest in our topic, and our topic is ultra-wideband localization for crane robot cooperation. Our team consists of myself, David, and Wanfu, and now we will show what our research project was about. Our outline is structured as followed. So we first start with the research problem, then we will describe our system, then we will describe what our experiment is about, then we will show the results, and then we will come to a conclusion. First, we come to our research problem. So with the rise of IoT and in industrial environment, more and more processes will be automated in manufacturing and logistics, and also the automation of material flow processes. However, in indoor environments, there is no access to global navigation satellite systems like GPS, for example. And therefore, ultra-wideband localization systems like the one we're using are a promising replacement for these GNSS. And the advantages of these systems are that they're relatively inexpensive, and after the system is installed in the environment, you only have to buy inexpensive tags that need to be localized for each robot. Another advantage is that you can retrofit these systems to older machines, and you can use commercial systems that are available. For example, the one we are using from Nokkala, and they are really easy to use and very simple. And therefore, we try to implement an ultra-wideband localization system for the cooperation between cranes and robots. And here you can see the overview of our system. So our system has three components. We have the ultra-wideband localization system, which consists of 4 beacons on the ceiling in the laboratory and 2 tags, one for the robot and one for the crane. And then we have a wheeled robot platform and an overhead crane. Now we come to our ultra-wideband system, and this is the only sensor we will use to control the robot. And we used a commercially available system from Nokkala, which is a Finnish company. And the system consists of beacons that you saw in the video already, that are on top on the ceiling, and tags that are placed on the robot and the crane. And this system measures the time of flight between an ultra-wideband signal that comes from the beacon, that will be reflected from the tags and goes back to the beacon. And this time of flight, with this measurement, you can calculate the position of the robot and the crane. The measurement data of these beacons will be sent to the Nokkala cloud, where we can retrieve the data and do our calculations and our control. And this all works in real time. Now we come to our robot. We used a wheeled robot platform, which is quite simple. And for our high-level control, we used a Raspberry Pi. And for our low-level motor control, we used an Arduino. And the robot has 2 motors for each side. Our control software is based on the Robot Operating System, which is the most popular software frameworks for robots right now. ROS code consists of nodes, which are, in our case, Python code. And these nodes are published or subscribed to different topics, which are messages between the nodes. And these nodes are, for example, sensors or motors or a control algorithm. For the ultra-wideband sensor, we have a WebSocket, which retrieves the measurement data from the Nokkala server. And this code also does filtering with an average of 10 samples to get a more accurate data. Then the navigation node subscribes to the location data and uses this to control the robot. we used a really simple control algorithm which has three modes, either forward, stopping, or backwards. And these modes are dependent on the location difference between the crane and the robot. So if the crane is in front of the robot will drive forwards. If it's under the crane, then it will stop. And if the robot is in front of the crane, it goes backwards. And then this navigation node will send PWM commands, which are the motor commands, to the Arduino, which then controls the motors. Now we're coming to our experiment. So we are doing a one-dimensional following situation between a robot and a crane. And the first step is that the crane is moved by an operator. Then the robot follows the crane is stopped, and then the robot should also stop under the crane. Then the crane is moved back to the starting position, and the robot should also follow to the starting position. Here you can see our results. So the results show on the y-axis the x-coordinate in millimeters, and on the x-axis we have the time in seconds. And this graph shows 5 periods, so 5 cycles of our experiment. And the blue graph is the robot, and the orange graph represents the location of the crane. And with this diagram, you can see that there's a slight delay of the robot before it follows the crane. So the crane starts, and then with a slight delay, the robot will follow. And you can also see that the robot overshoots a bit before it stops. And this is mostly due to our control algorithm, which is really simple and easy. And it also, this control algorithm also has some tolerances, which means that it's never completely under the crane maybe, but more in a radius that we defined, that we say this is still acceptable to be under the crane. In conclusion, our experiment results show that an ultra-wideband system can be used to automate material flow processes. For example, our process of a robot-crane interaction, and a slight delay and overshoot of the robot due to primitive control and filtering algorithm is still there. And for future research, we should improve the control and filtering algorithm to decrease the delay and the overshoot. And we should also increase the complexity of our cooperation process. So for example, we could do a 2-dimensional following situation. It would be harder, but it would be more realistic. And in the end, it would be good that there's a case study in a real manufacturing or logistics environment, and not just in the laboratory. In the end, we want to thank the team of Nokkela for providing us the system and for their amazing support throughout the whole project. And we would also like to thank Nilusha and Risto, our supervisors, and our teachers, Petri and Panu. And we want to thank you for your attention.